Hello and welcome to the fourth in this series of short demonstrations showing how Rational Team Concert, Rational Doors and Rational Rhapsody can help you in the process of complying to ISO26262 for the development of safety critical automotive products. In the previous demonstrations in this series we have examined how Rational Team Concert and our web-based process content helps with project management and governance for ISO 26262. And how requirements can be managed and worked with collaboratively across Rational Doors, Rational Team Concert and Rational Rhapsody. The focus of this demonstration is the implementation of the work item activity to develop a functional safety concept from a set of requirements using a model-based approach. The main tool that is featured here is Rational Rhapsody, detailing how it interacts and collaborates with Rational Team Concert and Rational Doors to help you comply with ISO 26262. Before we get down to Rhapsody, we need to understand the roles and the tasks that the main people will be carrying out in this particular phase of the development process. The two people that we're interested in are Dan, who is the developer, and Mark, who is the safety analysis engineer. And the tasks that they have to do are: Dan has to create the item definition, and Mark, as part of the hazard analysis and risk assessment, has to do things like the hazard and risk classification, determine safety goals and the ASIL determination. And these will all be captured in Rhapsody. So we can see the tasks that Dan has to perform by clicking on here and doing a search for the work items that are associated with him. At the moment we're actually in Dan's work area. So we can see that he has a task to create the item definition. We bring up that particular task. Because this task was generated from the RTC ISO 26262 work item template, it's automatically linked the work item description from the web content, and he can use this as guidance as to what he needs to do. As mentioned before, there are also links here to specific content around model-based or using model-based systems engineering for the item definition. Going back to the item definition, we can also see links which show which of the tasks that this particular work item depends upon, which is gather the pre-existing information which comes from Susan and relates to the managing the requirements. They are both children for task or activity 3.5, which actually relates to the item definition. Dan will be using a model-based approach to develop the item definition and functional safety concept. The first thing that he has to do when in Rhapsody is start to import requirements from Doors using the gateway. So open up the gateway. From here we can see the system functional requirements from Doors, and if we click on a requirement we can show that it relates to that particular requirement in Doors. So we're directly linked to the original sets of requirements that we've been working on. From here we can see that the requirements were imported into the system functional requirements package, and we can get a view on them, in this instance in the requirements table, which shows all the functional requirements at the systems level, their description and their requirement type and ID. Based upon these requirements and some high level work, we then start to develop a set of primary use cases. This, based upon being an adaptive cruise control system, is showing actors like the engine control management, displays and instrument panels, and cruise control settings. If we follow this down, I'll start to show how our requirements relate to the specific use cases, and these provide drivers for our further analysis. One of the tasks when building the item definition is to catch any preliminary architectural concepts that you might have, and we've done this in an item definition model. This is a very high level model which shows the interaction of the system with its actors, and based upon our original set of requirements and also our understanding of what the system might look like, we've created a very simple item definition which has a radar monitor, an adaptive cruise control element and a speed filter. This can be further detailed by going down and opening up the state chart, which captures some high level behaviour at this level, or we can go deeper down into some more detailed behaviour, the various states of the system and the events that are required to actually drive that behaviour. Now that Dan has completed the item definition task, you can go back into RTC and change the state from in progress to being resolved and then closed. This updates the task board, which details the state of all the relevant work items, and we'll see task 579 coming up under done. There we go. Task 579 has now been updated from being in progress to being complete. Going back to the work breakdown, the next task is up to Mark, who will be doing a lot of work around the hazard and risk classification, or determining safety goals, ISO determination, then the situation analysis and hazard identification. Mark, using the safety analysis profile, can generate a fault tree analysis, of which this is an example, based around the main hazard at the vehicle level, which is a vehicle crashes into an obstruction. By using the relevant AND or OR gates and the resulting conditions, this can drive out a set of basic faults in the system. To aid in automotive safety analysis, the safety analysis profile has been extended to cover specific safety analysis requirements for automotive. One example of this additional functionality is a table that behaves like a failure mode effects table, looking at the fault description, the item that it affects, the failure mode, the effect of the failure. But in this instance, it also covers the inputs, the severity, exposure and controllability, which are used to determine the ASIL. This information is actually captured via a set of tags that are associated with a particular item. Here we can see the ASIL and its contributing attributes. From these basic faults, we can then start to derive safety goals and safety requirements. And this shows all the safety goals and safety requirements for this particular problem around the adaptive cruise control. These safety goals and safety requirements are then pushed back into doors via the gateway. Here we can see them in the gateway. If I click on a requirement, I can then navigate back to doors, and we can see that the radar signal failure with an ASIL of B has been exported directly back to doors. Now that Mark has completed the safety analysis and pushed the safety requirements and safety goals back into doors, these provide the inputs for Dan to carry on and develop the functional safety concept. Here is the detailed architecture. It has the same elements as was used previously: the radar monitor, the cruise control and the engine control. But in this instance, to add safety, we have a radar arbitrator, which is looking at the difference between the left and right hand radar signals, and a vehicle speed arbitrator, we're looking at the input from two different types of sensor on the wheel and making sure that they're the same. The architecture is given a context by having an overview, or we can see it in the context of the radar sensors, a display, the environmental sensors, i.e. the speed sensors from the wheels, the brake control model and the instrument pedals. Further detail is added by capturing scenarios within sequence diagrams. This is just a single sequence diagram showing the scenario required to evaluate the accelerator pedal position and the various speeds and signals that are going between the elements. This behaviour is actually captured within the state machines, which are buried within the structure. This is the speed arbitrator, which is looking at the different input speeds from the sensors and ensuring that they're the same. Now that Dan has finished developing his functional safety concept, he needs to test it, and the way that we're going to do this is through some simulation. This is a test panel which we can use to inject signals and information and data, and also see information from the model. And we have just started the simulation. It's now been initiated with the cruise control off, radar sensors are OK. We can start to look at states within the model. In this case, the environment sensors. The sensor is okay at the moment, and we can put it in one of two fail states. First one is used to simulate when the sensor signal is not there. The second is when the vehicle speeds are different. It generates a sensor speed which is different from the first sensor speed. The other information that we're interested in is we're going to look at the cruise control. In this state chart, at the moment we're in the inactive state, but we will go into the active state later on. If a sensor failure is detected, it will then go from an active state into the safer inactive state where control is returned to the driver. As we're going through our scenario, the sequence diagram will actually record all the inputs and outputs as they occur between the various elements in the model. So the first thing that we need to do is we need to apply some pressure to the accelerator. I'm going to go through this single step through the model. It gives us a lot more control. You can see the vehicle speed increasing in line with the desired speed as the pedal pressure is maintained. I'm now going to turn the cruise control on, and we can see that the cruise control is on from this panel, and we can also see it within the state machine. So that is now active. Now going to inject some faults into the system, and we can see that sensor 1 has failed, and we'll start to see number of speed sensor errors are increasing, and it will take one more for the system to fail safely and the cruise control to go off. Now gone back to our inactive state. This proves the functional safety concept for safety requirements around speed sensor failure. Now that we have started to realize our safety goals and safety requirements through the functional safety concept, we can start to capture those safety requirements within another table which is showing our safety requirements, and from there we can start to allocate our safety requirements to functional subsystems, which is what is shown here. On the left are the subsystems, at the top are the various safety goals and safety requirements, and this is showing the trace between them. This drives down further because it now leads down to the ISO allocation for the various subsystems, which can also be captured, and this is what you saw on some of the architecture diagrams. And finally, these coverage and traces are then reflected back in the Rhapsody gateway. Here we can see the safety goal cruise control deactivation relates to hazard vehicle crashes into an obstruction, and as a resulting condition cruise control fails to deactivate. If we take this lower down and maybe look at our radar signal failure, you can see that it links in with the safety goal to identify obstructions, covers the basic faults radar failure and radar hardware I/O failure, and it's linked to the radar arbitration, which is the subsystem that can negate this fault. In this instance we've covered 100% of the safety requirements within this particular model. At the moment, of the system functional requirements, only 76% are covered. Now that we've completed the functional safety concept and showed coverage of all our safety requirements, this model can now be handed over to the systems development team where further analysis can be carried out along with the allocation of safety requirements to hardware and software components. Rhapsody can also be used for software development and testing using Test Conductor and Rational Quality Manager. In summary, this demonstration showed how we can manage an ISO 26262 project by showing the use of and collaboration between Rational Rhapsody, Rational Doors and Rational Team Concert, as we took a set of system requirements, developed an item definition, carried out a failure analysis to determine the ASILs, safety goals and safety requirements, and from this a functional safety concept. We ended up with a physical architecture. Further demonstrations in this series are expected to concentrate on the use of these feature tools along with Test Conductor and Rational Quality Manager to describe the software development and test phase and the systems integration and test phase. Thank you for listening.